मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
Before we go further, let us summarize what all we did in the last class about isoparametric formulation. Remember that we talked about isoparametric formulation as a very general methodology for a variety of elements. The elements may be plane stress, plane strain, solid elements and so on. So what we are going to do is to quickly summarize all the steps that were involved in the last class and then go ahead to evaluate the stiffness matrix as well as the right hand side, that is the load. If you remember that about 2 or 3 classes or even before, we had derived the stiffness matrix terms. So we said that the stiffness matrix can be written in terms of B transpose dB dV. So we started in the last class, actually we started there, and we introduced the concept of the natural coordinates and how mapping could be done. So now we transform this equation into an equation of this form, where psi and eta, if you remember, we introduced it as natural coordinates. Okay, please note that this J we are talking about is a Jacobian, okay, about which we will see in a minute, and that this symbol indicates that it is a determinant of Jacobian. There shouldn't be any confusion, it is not a matrix and it is just a symbol for the determinant of the Jacobian. We wrote down Jacobian as dou x by dou psi and so on, and then we went ahead to derive the strain matrix. So have a look at the strain matrix. The strain matrix has u comma x, u comma y, v comma x and v comma y. So in order to transform this into a strain matrix, we introduced a 1 0 0 0 0 1 0 1 1 and so on. Now we defined the Jacobian such that u comma x and u comma y can be related to u comma psi and u comma eta through a Jacobian. Just have a look at that and it will be clear that we introduced the Jacobian to I think there is a small mistake, I will just get back here, dou x by dou psi, dou y by dou psi, and sorry about that, I think dou x by dou eta and dou y by dou eta. Okay. So from this, okay, we derived that u comma x and u comma y could be related to u comma psi and u comma eta through an inverse of the Jacobian. So we did that in the last class and called that as gamma s. So ultimately when we stopped in the last class, we said that u comma x, u comma y, v comma x and v comma y could be related to u comma psi, u comma eta, v comma psi and v comma eta through a gamma matrix. We call this as the gamma matrix. So what is the whole idea of doing this? The whole idea of doing this is to replace the dependent of x in the B matrix to the dependent of psi and eta. In other words, B, a function of x and y, should be replaced in terms of psi and eta. So that is what we are trying to do. So we have come to a stage now where I can write out u comma x, u comma y, v comma x and v comma y in terms of my psi and eta. So what is that I am going to do here? At the next stage I am going to plug that in to this particular matrix. So you can now see this. So u comma x, this matrix will be replaced by this gamma matrix into u comma psi, u comma eta matrix, this matrix, this vector. How do I replace this? this is now replaced in terms of the n's, because remember u is equal to sigma ni ui and so on. So u comma psi, u comma eta and so on will be replaced by means of n's and d's. Okay. So this goes here. So you will see that let's call this matrix as dn. Okay, a part of it we called it as dn, let us, because we are completing it, let's call that as dn. Okay, then you would see that this is gamma into dn into d is equal to this vector which goes here. So that complete thing multiplied by these ones and zeros would now give me b. So in other words, epsilon is equal to this ones and zeros matrix multiplied by this gamma matrix, what we just now saw, multiplied by this dn matrix multiplied by d. So those are the three matrices that we would have in order to define d. Now we know that epsilon is expressed as b into d. So obviously b now becomes all these terms put together. Okay, all these terms put together now becomes b. Okay. Please note the difference between the dn which I have defined here and the same dn name which I have given in the previous class. Maybe if you want to avoid confusion, we can call this as bn total, because the difference is that it has 4 rows and the previous one had 2 rows. Maybe if you are a bit confused about it, you can give another name to it. But anyway, dn is nothing but dou n's by dou psi and dou eta. That is the matrix. So having done this, what is the next step? Just substitute this b into my first equation here. First equation here. So b transpose db. What is d? D is nothing but the stress strain matrix. We know about that already. Okay, for plane stress we know what it is. So we substitute this b into this equation. So we know all the terms here. Okay, in other words, we can write down that k as phi, say psi comma eta t j d psi, sorry, d eta. So we can write down k like that. So our next step is to evaluate this particular integral. Okay. Now this is a very happy situation, because the integral was a surface integral and volume integral, which was a bit difficult for you to derive, especially when the shape is quite bad. Now what is that we have done? We have replaced that by means of a psi eta coordinate system, and the coordinate now varies only from -1 to +1. So what is the advantage now? The advantage is that we can resort to what is called as numerical integration. We are going to see what numerical integration means. So I hope things are clear now. We are now in a position to calculate stiffness matrix. Please note, again a reminder, that whatever be the shape, okay, whatever be the quadrilateral, we just derived it for quadrilateral, whatever be the quadrilateral, whether even if a quadrilateral is regular or whether it is irregular or whatever be the shape, okay, the procedure is the same, because we map all of them into a lovely square in the psi eta coordinate system. So the procedure becomes quite well established, and it's very easy now to write down a computer program. Okay. Now let us look at, quickly summarize what we are going to do with respect to this numerical integration. What is numerical integration? Let us look at an equation of the form, say integral minus 1 to plus 1 phi d psi. Now, we can evaluate this by different schemes, numerical integration schemes. Now, what are these schemes? These schemes are called as Gauss quadrature scheme, okay, and then Simpson's rule, for example, is one of the numerical integration schemes, and so on. Usually in finite element analysis, it is the Gauss quadrature rule that is extensively followed, though there are other rules like Newton cotes and so on. Gauss quadrature rule is what is usually followed. What does this rule say? The rule states that if you evaluate phi, what is phi? Phi is now a function of psi. If you now evaluate phi, which is a function of psi, at certain designated positions, okay, and multiply it by weight and sum them up, then that result, whatever you have, would be, okay, very accurate depending upon how many positions of these designated places you include. Let us look at the simplest one dimension case. Let us say that we are trying to evaluate that kind of curve. Okay. Let us say that we are trying to integrate this between minus 1 to plus 1. Okay. Now, in a one point quadrature rule, the position at which we are going to evaluate this is given by that position where psi is equal to 0. Obviously, this is that our I, and that is this psi. Sorry, that is a phi and that is the psi. Okay. So, the designated position here is psi is equal to 0, right. And what is it that you get here? And yeah, that is nothing but phi at psi is equal to 0. Okay. Let us call this as, say, phi 0. If I now ask you what is the integral value of this curve by evaluating that function phi at a position called psi is equal to 0, your immediate answer would be that, look, that is only the area under the curve, and so you can write this down as 2 phi 0. So, in other words, what does it mean? It means that this 2 is the what is called as the weight function. Okay. This is one point quadrature rule. You can have more than one points as the quadrature rule, and let us see what the other rules say. Now, let us look at 2 point quadrature rule. 2 point quadrature rule says that you evaluate the same function at 2 positions, okay, at 2 positions, not now, no more at the center, no more at this position. So, at 2 positions. These 2 positions are given by, okay, plus or minus 1 by root 3. Right. So, you evaluate this function at 2 positions. What do you mean by evaluate the function? Now, phi is a function of psi, right. What is that you do? You substitute the value of psi to be plus 1 by root 3 and then again minus 1 by root 3. Okay. So, you will get at 2 positions the value of phi. Let us call the positions as, say, phi 1 and phi 2. The numerical integration rule states that this integral can be written as W1 phi 1 plus W2 phi 2, where W1 and W2 are the weights, okay, and they happen to be 1 in this particular problem or in this particular rule. So, this is called as 2 point quadrature rule. Okay, you have also 3 point quadrature rules. Okay, the 3 points are, okay, spread, at 3 different locations, and again these locations are given in terms of psi and eta. The locations happen to be 0, plus and minus root of 0.6, plus and minus root of 0.6. So in other words, the 3-point integration rule states that one point here, one point here, and one point here. Okay, these are the 3 points at which the value of phi is evaluated. Okay, and the value of phi at psi is equal to 0 plus root of 0.6 minus root of 0.6. What are the weights here? The weights happen to be 5/9 for this position, 8/9 for this position, and of course 5/9 for this position. So in other words, now if I use 3-point quadrature rule, then this integral say I now becomes W1, which is say 5/9 into phi1. Phi1 is the value of phi at minus root of 0.6 plus 8/9 into phi2. Phi2 is the value of phi at psi is equal to 0 plus 5/9 into 5/9 into phi evaluated at root of 0.6. So W1 phi1 plus W2 phi2 plus W3 phi3 is what we get, okay, as a 3-point quadrature rule. You can keep on extending. In fact, there are tables that are available. I am not going into the details of it. You can have 4 points quadrature rule and so on. I am not going to go into the details of it. Nevertheless, it is important that the accuracy of it is well understood, in the sense that whenever you have root of 0.6 and you do not want to calculate it, okay, or you want to calculate and put it, you do not want the computer to calculate it, then this root of 0.6 should be given to a very large number of significant digits, because that will affect our results. Okay. Now what the question now is, what is the quadrature rule that you are going to use or you should use? Before we come to that, let us now extend our concept to 2D as well, okay, because my K matrix which I had and which I transformed, okay, is now in 2D. Maybe we have to extend it to 3D as well, okay. So let us look at 2D, because if I understand 2D, how to do 2D, then 3D extension is quite simple. So in other words, what is that we are going to look at? Instead of what I had, instead of say now K is -1 to +1, -1 to +1, some 5, okay, T J d psi d eta, and phi is a function of psi comma eta. What is phi psi comma eta is always a confusion with students. Phi psi comma eta is nothing but B transpose dB calculated at psi and eta. Now let us say that that is the element after the transformation into the natural coordinate system. So now what is the rule that we are going to use? Say for example, we use a 2/2 rule. We used, okay, 2 integration points for one dimensional case. Now we are going to use 2/2 rule, which means that I will have totally 4 points. How do I get 4 points? By extending that psi plus or minus 1/√3 and eta plus or minus 1/√3. So I get, so in other words, that this line and this line are such that this is equal to plus 1/√3, minus 1/√3 and minus 1/√3 and so on. So in other words, the coordinates of this is minus 1/√3, minus 1/√3, 1/√3, minus 1/√3, 1/√3, 1/√3 and so on. So I get 4 points. Then how do I now evaluate the stiffness matrix? that is evaluated as 2 sigmas I j, both of them vary from 1 to 2, okay, phi calculated at these positions, 4 positions, or let me call it phi I j wi, two sigmas, okay, let me call wi wj, and phi calculated at psi I eta j. I and j, I and j varies from 1 to 2. So I will have now 4 points, or in other words w1 into w1, phi into phi calculated at phi, not into phi calculated at psi 1 eta 1, then w1 w2 phi calculated at psi 1 eta 2. What is psi 1 eta 1 and so on? These are the points, that is psi 1 eta 1, which is minus 1 by root 3, minus 1 by root 3. What is psi 1 eta 2? That is this point, and so on. Okay. So you calculate at these 4 points, multiply by the weights, okay, then, or rather this point, and so on. So you get, or in other words, you calculate the size at all the 4 points, and the weights happen to be for this problem 1, and so wi into wj into phi's at these 4 points give you the value of k. Okay. In other words, what is that we do? We calculate k at each of these points and then sum them up. Okay. That is what we mean by stiffness matrix. Is that clear? So maybe you can have a look at this whole thing again, okay, what all we did. Okay. So the stiffness matrix calculation becomes quite nice and easy. Now there are 2 other things that we have to notice, or we have to do, that is quite involved. Okay. Let us see what is the other things that we have to be involved. I hope that I followed all the symbols what we did in the last class. Yeah. Okay. Now what are the other things that we have to do? We have to calculate the right hand side. In the right hand side, we have basically 2 types of loads. Okay. Now apart from the concentrated load, the body force and the surface force. Body force is not a problem because the procedure is exactly similar, but surface forces create certain trouble. What is the trouble that we are going to have with the surface forces? Now let us look at this element. Let us say that is the psi eta coordinate system. Let us say that this element, okay, sits on the boundary of a component. Say for example, that is the boundary of the component, and so on. So in that component, or in that element, we have defined a surface force or surface traction, pressure, whatever we call it. Let us say that we have given a pressure of say phi x and phi y, okay, in this particular surface. Now what is it that I have to do? I have to now calculate the right hand side. What is the right hand side? If you remember, the right hand side is n transpose phi ds at s, okay, or in other words, we have to evaluate a surface integral which is n transpose phi dx. This phi is given as phi x and phi y. We know what is n, we have been through it for quite some time, and hence we know what is n. So the whole idea now is to calculate what is n transpose phi ds. how are we going to calculate it? Because we are into what is called as natural coordinate system. We have already transformed the element into a natural coordinate system, and hence my job is to now transform this equation as well to the natural coordinate system. Or in other words, my first job is to recognize that the phase in which I have given the load happens to be what? Eta is equal to -1 in the natural coordinate system. In other words, symbolically writing it, if I write this as the natural coordinate system, right, psi, yeah, eta is equal to -1, right, and hence eta is equal to -1. That is the phase in which I have given the load, or in other words, here is the phase in which I have mentioned phi x and phi y, right. Okay. Now, how am I going to evaluate this? In other words, my equation now actually becomes, okay, sorry, evaluating it as at d psi. This implies, okay, I shouldn't say equivalent, but there are a lot of things I have to do in order to get to this. Now, what are the things that I have left out? I have left out quite a few things. They imply, they are not equal, because I have left out certain things deliberately. What are the things that I have left out? I can't straight away convert it like this. Okay, though I want to have a equation of this sort, I can't straight away do it. First of all, let me convert this surface into line. Why is that we have to convert the surface into line? Because we are now talking only about a two-dimensional situation, a plane stress example. So my first step is not to write like this, though ultimately I want to do it. Okay, first step is to say that, look, integrate it, say along the length of the element. Let me call this as 0 to L n transpose phi, say dl. That is my first step. What is n transpose phi dl? How do I convert it? Or in other words, I can do that as -1 to 1 n transpose phi j d psi. That is exactly how I do it. Okay. Now, what is j? Determinant of the Jacobian, or the Jacobian in this case, what is j? And how do I calculate n? Usually these are questions which are confusing to the students. The answer is very simple. How do I calculate n now? Because you may wonder, n had psi and eta. How do I calculate n now for one-dimensional case from my previous n's which I have? How do I calculate that? The answer is very simple. In the previous n's, what are the n's you had? 1/4 into 1 minus psi into 1 minus eta, plus that is for n1, n2 you had 1/4 into 1 plus psi into 1 minus eta, and so on. Okay. So in those n's, just substitute eta is equal to -1. So in other words, what we mean is this n or n transpose is calculated at eta equal to -1. So that problem is solved. When I substitute eta is equal to -1, my n purely becomes a function of psi, no problem. So straight away I can calculate. Phi is a value, phi x and phi y, that is, in other words, the x and y direction, they are given. Okay, that is not an issue, because we may, let us for the moment assume that they are constants, okay, or else we may have to do something else. Let us not confuse the issue. Let us say that they are constants that are acting in the x and the y direction, okay, or else we have to interpolate them as well. Let us not worry about that. In other words, phi x is constant throughout this phase, phi y is constant throughout that phase. So they are just written there in terms of numbers. So, the first term is known, second term is a vector, it has 2 entries or 2 rows, 1 column, and next is j. Once I do that, once I calculate now j, my calculation of this integral becomes very simple because I can use numerical integration. So, the question is now, what is that j? Let us take a pause and see how to calculate that j matrix. Yeah. So, have a look at this and see for a minute as to how we can now calculate j. In other words, we have to very carefully define what is j, the Jacobian. After all, what is that we have done here in this equation? We have replaced dl by j d psi. So, what should be j? J should be dl by d psi. So, we have to find out now dl and write it in terms of d psi. That is all we have to do. Now, once we do that, in other words, once we calculate dl, write down dl, okay, then it is very simple for us to calculate j. Now, what is dl, or how do you calculate dl is the question. Now, dl can be written as, okay, let us look at that figure. Have a look at this figure and see how we can write down, have a look at that figure and see how we can write down dl. Okay. Now, we can write down dl in terms of, okay, dx by d psi, okay, whole squared as dou x by dou psi whole squared plus dou y by dou psi whole squared whole power of d psi. Okay. Now, how do I get dou x by dou psi and dou y by dou psi? That is very simple because I know that this can be written in terms of n's. Okay. So, when I now substitute dou x by dou psi and dou y by dou psi, where x is equal to ni xi, and then simplify this, I get that dl is equal to L by 2 d psi. Okay, I am not going to do that exercise, that is very straightforward, just substitute it, and you will see that dl and d psi are related by L by 2. And now, what is this L by 2? L by 2 is nothing but the Jacobian. So, with that result, we can write down our previous expression for n transpose phi j d psi as minus 1 to plus 1 n transpose, phi remains the same. Now, j becomes L by 2 and we get d psi. Okay, what is L by 2? What is L? L is the length of that element, length of this particular h we are talking about. So, that is the L, and hence, okay, this expression is useful to determine the RE, R due to pressure. Now, please note that phi is actually a vector, phi x and phi y. Okay. So, correspondingly, this is also a vector and it has 2 entries. I need not tell you what n has, you can very easily find out because I have already given you a clue that this n has to be calculated with eta is equal to minus 1. So, in other words, what is essentially, or what is the crux of our approach? Our approach has been that we not only calculated the stiffness matrix by transforming it to a natural coordinate system and then resorting to what we call as the numerical integration, we also calculate, or we can also calculate the other REs, okay, or the R's, or the right hand sides to be more precise, or in other words the load due to the surface traction or pressure can also be calculated by means of this natural coordinate system by transforming the equation. What is this equation? How did we get? Please note this equation we got it from our virtual work principle. By transforming the equation which we got from the virtual work principle onto, say, the natural systems or natural coordinate system from where psi varies from -1 to +1. So that in a nutshell shows that all the aspects, whether it is the stiffness matrix or whether it is the force terms, all these things can be calculated in a very consistent fashion. Okay. Now there is always a tendency to replace this phi by means of dividing that or multiplying this by total length, okay, and then dividing it by 2 and putting it at 1 and 2. One of the things you should notice, there are two things actually, not one, two things that you have to notice. One is that you should always look at how phi is defined. Okay. Now please note that in this particular definition we have assumed that phi is defined per unit length. If phi is not defined per unit length, then you will have to now look at t as well, thickness as well, okay, so that you convert it into unit length. Why is that we are emphasizing on unit length? Because we are now in a plane, okay. So it is important that you look at how phi is defined. If phi is defined anywhere else, then your units on the left hand side and the right hand side should be consistent. Say for example, we have defined a t in the left hand side, okay, for k, then you should also have a t if it so happens that you have defined phi as well as t. So in that case you have to multiply this by t as well. Okay, please note, this is a very simple thing, but people make a mistake. Please note how phi is defined, okay, and so that the units what has been given there is consistent and thickness is taken care of properly by the units that are given for phi. So that is that's a very important thing. And the other one is that this is only an example for eta is equal to -1. So happens that the same element may be in the other end, okay, at the other side of the boundary, and so that we may have to apply pressure not at eta is equal to -1, but say psi is equal to 1 and so on. So you have to be properly accounting for the surface where we give this pressure. What is the surface that we are interested in? Where is that we are giving pressure? And accordingly you have to do this derivation. Thirdly, if the pressure does not happen to be constant, okay, then if it varies, say varies from one end to the other, then you have to introduce linear interpolation even for phi's as well. So that makes the problem slightly more complicated but not difficult, it is very straightforward. Only thing is that in that case you have to now introduce interpolation for the phi's as well. There is always a tendency to lump these loads. We will see later in the course that lumping may be very dangerous. It may not be consistent with the result we have got. In fact, these loads which we have calculated by such a very rigorous procedure of integration are called as consistent nodal forces. They are consistent with our other definitions. So they are called consistent nodal forces. You have to be very careful to not to miss out this and just to divide, say for example, if length is equal to some 5 and if the load say phi y acting is say 5 per unit length, so you can't multiply phi into phi 25 and then divide it by 2, 12.5, 12.5 and so on. Yes, it will work for linear elements, okay, but for other higher order elements this kind of procedure won't work. So even when you write a program, even if it works for some cases, it does not mean that you should not do this integration. You should go ahead and do this kind of integration, and if you want to write a code, and then this is what should be implemented, and that is very important. Okay. A very detailed account of how to write the code for this has already been given by Owen, I think Hinton and Owen in a book on finite element programming, where you will see that a very detailed exposition of how this code can be written is given. Anyway, for our course it may not be right now necessary to go into the details of how programming is done, but nevertheless it is nice to know that these things are important. Okay. What is the second issue? Now we have now looked at what is called as a quadrilateral element. What are the other types of elements which are very popular and which are important? Triangular elements. Triangular elements become very important. Why is that the triangular elements are important? Because most of the mesh generation codes or mesh generation packages have triangular or tetrahedron, its three-dimensional counterpart, as a mesh generation facility. Now today there are a lot of mesh generators which can do quadrilateral elements, so there is no problem, but hardly there are any mesh generators which can do what we call as a hexahedron element, and hence it becomes important that we know how to handle triangular elements. Basically there are two ways in which triangular element stiffness matrix are determined. But by the way, we already noted one thing important about triangular element. If you remember that we said that triangular elements are constant strain triangle elements, or in other words we said that the strain happens to be a constant in a triangle. We illustrated this with a very simple example. We said that, what is that we said? So we said that, let us say that we will call these three nodes as 1, 2 and 3. So what did we say? We said displacement can be a0, a1x plus a2y, can be written like this. So we said if you want to calculate dou u by dou x, what is that we get? A1. So what does it mean? It means that when we express the displacement like that as an interpolated value, then dou u by dou x, okay, becomes a constant. It does not matter whether we replace this a's by the degree of freedoms at the three nodes 1, 2 and 3, okay, it does not matter because the basis is only a linear interpolation formula like that, and hence dou u by dou x becomes a1 and so on. So the strain within that element becomes constant. Now what is the trouble with this? We have already seen this with an example. We saw that because of this, okay, we have to have lot of elements, especially when there is bending that is involved. There are lot of elements that we have to use in order that the bending exercise or when an element or when the component bends, the bending is properly taken care of. So I am re-emphasizing it basically because I have found lot of mistakes during modeling. Why is that there are a lot of mistakes? Because it is very easy to do what we call as free meshing. Take a three-dimensional component, mesh it with the tetrahedron and just go ahead and finish the problem. But if you do not do a proper mesh sensitivity as we did on the other day, then you are going to be in trouble. With all these drawbacks, still we have to learn about triangular element and its three-dimensional generalization, which is the tetrahedron element. We will concentrate only on the triangular element because what we are talking about in the triangular element is very similar to the tetrahedron element. So there are two procedures, the two ways in which you can calculate the stiffness matrix. Procedure number 1 is to collapse two nodes in a quadrilateral element. What do we mean by that? So let us say that I have an element like this. Okay? Now, simple element, just to illustrate how we collapse. So let me call this as say 1, 2, 3 and 4 anticlockwise cells. Okay, fine. Now I can develop a triangular element following exactly the same procedure, whatever I have done so far, exactly the same procedure, by collapsing 1 onto 2, and which results in an element something like this. Okay, whatever be the shape, it does not matter. What do? I collapse x1 to x2. What do I mean by collapsing? I simply mean that I give the coordinates of 1 and 2 to be the same. x1 is equal to x2, y1 is equal to y2. Where do I do that? I do that in my expression for x and y, first step. So, what is that I mean by collapsing? By substituting that x1 is equal to x2, y1 is equal to y2 in these two equations. Is that all? No, because we are using isoparametric formulations, and hence we have similar values for u and v as well, So u and v are again written, and this collapsing exercise is done. So I can say that it is 1, 2, 3 and 4. Collapsing exercise is done there as well. So u1 is now the same as u2. So in other words, when I do that, what essentially I get as degrees of freedom? Simple, u2 v2, u3 v3 and u4 v4. So these are the degrees of freedom that I get. So one way of calculating the stiffness matrix is by doing this collapsing business. This is very simple, and I will do that in the next class by taking an example, okay, simple example, and following all the steps that I have done in this class and the previous class. The other way of doing it, there is another way of doing it, is by following what is called as area coordinate system. Area coordinate systems. Okay. So the area coordinate system is some sort of a generalization or an extension of the natural coordinate system which we have in place right now. So the second way of doing it is by area coordinate system. Now whatever we have been talking about so far has been for linear element, but that is not sufficient. I said that the interpolation values can be of a higher order polynomial. It can be quadratic, it can be cubic and so on. Now whatever we have been talking about, whether it is the quadrilateral element or whether it is a triangular element, it is possible to raise the polynomial level or polynomial degree, okay, from a linear exercise to quadratic, cubic and so on. So our exercise, next exercise, is to complete the triangular element, okay, by collapsing and get into this area coordinates, and then extend this whole exercise to a higher order element, which is not very difficult. Now I am not going into each of the elements. For example, continuum elements of 3D, I am not going to the details because it is exactly similar. I leave that out as an exercise. Okay, so we will meet in the next class and see how do we tackle this triangular elements.